Hello and welcome. This will be the first video in a series of videos on HackTheBox machines and challenges. So today we're going to start with Ellingson, which is a medium difficulty box that involves some basic web exploitation and some binary exploitation later on. So first we'll get started here. As always, the first thing I did was run an nmap scan of all ports and services on the box. So pretty standard, just two services up, 22 and 80. So we've got a web server running, which means I also kicked off a dirbuster or dirb scan. So there, nothing really stood out there, not too much going on. So let's actually check out the website itself. Alright, so it's a homepage for a company. Looks like they've got some news articles here, some teammates here. That's just boilerplate down there. So see if these articles are actually, yep, they're different pages. So they're saying an intruder recently broke in and they're demanding a ransom. Okay. More information about protections about brute force and intrusions. So hopefully we don't get locked out trying to do anything later on. If we were sending a lot of requests, we'll see what happens. Network activity. So there's a hint here about some possible passwords, which we can make note of for later on if we need to guess any passwords. So far there's not much to this website, not much in that dirb scan. The only thing I noticed so far is that there's a integer value up here in the URL for the current article that we're on. And so my thought was maybe there's some kind of injection or something possible with this. So I just matched my numpad and hit enter. And shockingly, we get to a error page. And what's great about this is the workzug traceback interpreter, which is used by Python web frameworks like Flask for debugging basically. And so it's not meant for production at all. And what's great is before they added the pin, you could just click this and run any Python command. And I guess it's an old enough version that they don't have that pin in place. So this is just like any Python shell you'd get on your machine. So we can start running arbitrary Python commands, which means arbitrary shell commands as well. So we'll import the subprocess library so we can run commands on the system. I'm going to see who we are first of all, and note I need to pass shell equals true in order to just pass a command in quotes like that. Normally it expects an array of commands and arguments. And we also want to see the output, so I'll send it to a pipe. Alright, so our user is Hal, H-A-L. Let's see what they have going on in their home directory, see if user.txt is there. Looks like there's no user.txt yet, so I guess a different user will have that. But there is a .ssh directory, so that means maybe there's something in there we can make use of. So it appears there would be. There's authorized keys. There's a private key and a public key. So we can try to grab that private key, see if we can just SSH in with that. I'll just cat it out of there. Pretty easy. So here's a private key. You can see here that it is encrypted, and so that means before we can use it we need to crack the password for it, or passphrase. And I went ahead and did this my first time through, and I wasn't able to crack the password using rocku. So that wasn't viable, so must have to go on to a different method here. Since there is an authorized keys file here, we can probably just write our own public key to this, our own SSH public key, and just SSH on, no problem at all. So to do that, I'm going to open the file with Python. You could also just use another shell command to echo it to the file or something, but this is easier. I'll open it in append mode since there's other content to the file, so I don't want to clobber that. Alright, I meant to assign that to a variable. Oops. So f will be that file, f.write. new line at the end, and I'll close that file to ensure it's flush to disk. And now I should be able to SSH on, and I'm specifying that key because I generated one for this box specifically. And we're in as hell, and as before, there's no user.txt here, so we need to try to move laterally to a different user in order to get that, most likely. So I'm just going to do some basic enumeration checks on here. See if we can sudo at all. Probably not, since we're getting asked for a password, which we don't know anyway. We can also see what groups we're in. So we're in the ADM group, which is interesting since that's usually for viewing logs, sometimes with sensitive information in them. So let's take a look at var log. We're able to read auth.log, syslog, and some other files. So nothing too interesting in here. We can just see that some users have been logging on. Notably, Margot and the Plague have been logging on. Nothing else in here. I'm just going to go out on a limb and grep recursively for the string password. Alright, so there's some hits. You'll note here there's actually I think a bcrypt hash for basically Etsy Shadow. And I went ahead and cracked that earlier, and it just comes out as password123, which did not work for any of the users on the box. I tried them all. So that was just a red herring there. Nothing else was interesting in this grep. So that might be a dead end for now. See what other processes are running here. Again, not too much going on. There's the web service we got in with. That's about it, though. Alright, so since we're in that group, let's look for files or directories that we can read or write to that aren't normal. Alright, so the first one should stand out big time here. That's a backup of the Etsy Shadow file, and it's readable by us. Alright, so we've got passwords now, or at least hashes, for all 4 users on the box except root, sadly. So I went ahead and threw these into hashcat, and the only one that returned anything was Margot. And the password for Margot is I am God $08. So we should be able to SU as Margot. Oh, I don't know why I put the password at the end there. Oh well. Right, sure. Yep, so now we're in as Margot, and there's user.txt, finally. Alright, so there you go. There's user.txt. Now it's time to move on to privesc to root. So same thing as before, I'll check if we can sudo. Doesn't look like it. I'm going to look around here. There is another private key in here, but I think it's either encrypted. Yes, it's encrypted again, and that one didn't yield anything for me either. So pressing on, I'll check for any setuid binaries on the box. Specifically files with permission. Anything that starts with a 4 in the first octal digit, meaning it's setuid user. So we got some standard binaries here, but one should also stand out right away. User bin garbage. No idea what that is. So if we run it, it prompts us for a password. We'll try our Margot password. That does not work. And it's a binary, so we can't just look at the script or something and find the password. There's some actual binary exploitation involved in this one. So I went ahead and pulled back that binary and ran it through a decompiler. And we can actually go through and look at what it's doing. So there's some simple functions here to just print a string. nothing too special going on. There's an unused function here, meaning that it's not called anywhere else in the program, so it's probably just there to provide us with some gadgets for rough exploitation, or perhaps to import some extra functions that might be useful. There's a function here to check user, and it looks like we're already getting past that since we didn't end up with that error. Had we run this binary as the first user, Hal, we would have gotten the not authorized error and the program would have exited, but now we're Margot and we should be able to run it just fine. So here's a function here that's actually checking for a password. So if we run this through the program, alright, we're actually into the program, worm control application. So as we saw in the decompilation, there's just some simple functions here that just print things out. So nothing special there. So looking at this, here's the main function which has the main loop in it with the main menu. So not too much going on. The only user input here is that there's an integer being read in, so nothing interesting there. The only thing that should stand out in this entire program is the call to get, which is putting standard input, basically user provided input, into a buffer that's 100 bytes long. And so that's likely our entry point for some binary exploitation. So let's see what kind of security features are enabled in this binary. Looks like we just have to worry about no execute and some rel-row. That's fine. There's no stack canaries and there's no pi, so that makes our time a little easier. So as you can see, there's a bunch of functions here that are actually imported into our PLT. I don't see system or an exec, so we won't be able to do that directly. So it's likely that for this one we're going to need to leak the address in libc of system so we can call it. Alright, so let's start our exploit script here. So when I first ran through this, I actually had trouble getting the exploit to work on my local machine, mainly due to problems with pwn tools. Actually, it wasn't really the way the exploit was set up. It was just something weird about the reading and writing from standard input and standard output. So we're going to go ahead and just set it up to run against the remote binary right away. And that way we won't, think it works with our local machine and it doesn't actually work on the remote one. So we're kind of better off doing it this way, even though it's a little slower. So we can use pwn tools SSH tubes. And we'll set up the process from that SSH tube. Set up our context. Alright, so start to put together some variables here. I'll save this password. It doesn't seem like we need to use it. Let me double check that real quick. Yeah, so in theory we shouldn't actually need to put the password in, since as long as we get to this return down here, which we will no matter what, it's fine. So we'll try it without first, but I'll just keep it on standby. So our first step here is we're going to have to leak the address of system in libc using a function that we already have imported in the PLT and GOT. So any of these will do. I'm going to use puts since we'll be using puts anyway, and it's just easy. So I ran objdump-r, which here shows me puts is at this is the GOT offset, or GOT, this is the GOT address of puts. So and we'll also need to define that in libc on the target. So you can see here, this is the offset and the target's libc to puts. And we also want the offset to system because it's the function we're actually looking for to call ultimately. And so system is at this address, or this offset rather. So I'm going to open this in GDB just to take a look at some of the offsets. You can see in that source file that the buffer was 100 bytes. But it'll likely be longer than that since we need to actually get to the stack pointer when it returns. So we'll use GDB for that. And I don't know if there's a way to save this in Jeff without copying and pasting it to a file, which is kind of a pain, but Jeff is nice otherwise. Yep, so we're going to run this binary with that as the input. And as we expected, it should segfault. Since this is x86-64, we're not going to see our payload in the RIP yet because it's not a valid address. So instead, we'll notice that RSP actually points to what will be the next instruction, basically, after the return. So if we want to find this, we need pattern offset of that. So this is saying here that if we are overflowing that buffer, whatever is at offset 136 will be the address we return to when we get here. All right, so that's going to be our offset we want to use for our overflow. And we can just do a bunch of A's. And so since we're going to try to leak the address of puts in the GOT, we're actually going to want to call puts and print out the address with it conveniently. So I also need to find the address of puts in the PLT. And one way to do that is just to dump the binary and grep out puts. And so this address here is where it is in the PLT. We can also do it over here in GDB, but that actually returned the address in libc, so that's not useful right now, but we can turn that off as well if we needed to. So we have a few of the building blocks here. We also need to actually put some gadgets in order to call our puts the first time. So I'm going to use Wropper for that. And we need to supply a single argument to puts, which is pretty easy. And the first argument in x86-64 comes from the RDI register. So I'm going to search for any gadgets that pop to RDI. So there's one here. Perfect, nothing else in there but the pop and the ret. Alright, so we'll start off with just seeing if this works. So we'll put together a basic payload. Our payload equals the overflow plus the pop RDI. And that's going to pop whatever is on the stack next. So we're going to actually put the address of puts in the GOT. And we're doing this because at this point, puts has been resolved to the libc address, and so if we read whatever is at this GOT's address, we'll actually see the address in libc as a result, if that makes any sense. So this should result in, oh sorry, I need to actually call puts as well. Alright, so also puts PLT. Since we're going to call the puts function, and it'll use whatever is in RDI at the time. So let's give that a shot. I actually have to put something in there first to send it. That'd be good to do. And we know it's going to prompt some other stuff, so I'm just going to put in a receive until. And this was the part I couldn't get working on my local machine. It just wouldn't receive anything when I tried this, but must have been a mistake I made or something. So we'll send that. It's going to return back the access granted. And then after that, it's going to actually send back our leaked address. And so once we receive that, I'll print it out and display the value of it. Alright, so let's give this a try. You know, it would help to actually receive. No, we did. Okay. So it looks like we're actually getting 7 bytes back. which is fine. So I couldn't figure out what I was doing wrong, but apparently things weren't working here because I was not, after I was calling puts, I guess, I mean, obviously the program didn't have anywhere else to go after the ROP chain, so it was dying, and it was causing my output, my puts at libc to be returned at all 0, so I was confused about that. So I just went ahead and found the address of main in the PLT and added it here as a variable, and adding it to the end of my payload. And now it works most of the time. It seems a little, oops, shoot. Seems a little inconsistent still. Sometimes it returns null anyway, but I don't know why I called it that, but it doesn't make any sense. So now if we do that, we should most likely get an address, and there we go. So this is the address of puts in libc. So, and this will be different every time we run it since there's ASLR on that system. And it got 0 again. I don't know what's up with that. But yeah, we have a different address. You can see the last byte is the same, but you can tell it otherwise it's different. So that's the address of puts. We just need to find the address of system, and we earlier we grabbed the offset in libc of puts, which is right here, and we also have the offset of system. So if we take this address and we subtract the puts offset, it'll get us to the start of libc, and then we can just add the system libc offset and we'll be at system. So pretty straightforward, really. Alright, so that's stage 1. We need to now do stage 2, which is actually putting it all together and using this leaked address to do something, which is calling system. So libc, we're going to interpret that address as an integer. And we'll subtract that from the offset of puts in libc. So this gets us to basically the base address of libc. So now all we have to do, system in libc equals that offset we calculated plus system libc up there, which is, I guess we shouldn't, no, it's not called offset, it's called libc. And these shouldn't be packed already. We'll unpack those so we can do it down here after we do the math. Alright, so that's the offset to system. And this will actually give us a real address, and so we can print this out if we want to see it. And so we can try this out just to see what it looks like. Hopefully I did all my conversions correctly. Yep, so I did. You can see here, this is the address of system in libc. So now we just have to call it. And so since we called main up here again, you have to go through the whole overflow again, so it's not too bad. Overflow, and we're going to load this up similarly to last time. We also need to find, I forgot about one thing, we need to find bin sh somewhere. And so we'll look in libc. So we can do strings atx of that libc instead of typing it, I just like to grab it from here and grep for bin.sh. Alright, so there's one, and it's there, that address. So same way we got the address of system, we can get the address of bin.sh. Just to verify that's working. Yep, so there's the address of that string. And so now we can do our stage 2 and actually call things. So again, we need to pop something into RDI, and in this case, we're making arguments for the system function. So system takes one argument, and that's the shell string basically that we're going to execute. So we need to fill RDI, the first argument, with bin.sh. So just put the address to that, and then we can do system's libc address. And so repeat this whole thing with sending the payload, and we can try to go interactive after that. So let's give it a shot and see what happens. Oops, so we got the 0 again. We'll just run it again. That's just bizarre. Okay, so we got our addresses as expected this time, all 3 of them. We got down to where we called interactive. We got an EOF, so we have no shell. Nothing works there. So there's one problem we haven't addressed yet, and the thing is that binary was set UID on that system, right? Although the problem is when you call a binary that's set UID, you won't necessarily run as the owning user unless you specifically request it because of effective UID versus real ID. It'll probably keep the real ID and not use the effective real ID provided by the set UID bit. So in this case, I'm going to want to call set UID, the set UID function, in my ROP chain in order to make sure my effective user ID is set to 0 and remains so. So like before, we're going to find that function in libc. So I did that earlier with readelf. I guess not anywhere in my history. That's fine. And if we look at the setUID function, it takes one argument, the UID, so we'll just have to pass it as 0. Pretty straightforward. And there's setUID function here. That's the offset in libc, like before. Let's see how that works. Yep, okay, so we got that address as well. And now we just have to add it to our second ROP chain here. So we need to use this pop RDI to put 0 in RDI. Just give it a 0 like that. And we'll call setUID libc. Then we'll call pop RDI again to fill the bin sh for system in there. Oops. That looks good to me. Okay, so what I do wrong now? Oh, I know what I did wrong. Huh. If anyone caught that, I was using the wrong libc. So when I grabbed some of those offsets, I was using my Kali libc instead of the remote libc because I forgot where I was. That's fine. I'll just check several of my offsets since I don't remember where I went wrong. Puts 809C0. That one's good. System is 4F440, that's correct. Set UID E5970, that's definitely wrong. And then I need to do my graph as well for bin sh. Also very wrong. So even though we had this stuff wrong, we still needed to do that set UID part. There we go. Okay. Who am I? We're root. ls root cat root.txt. Alright, so that's it at this point. Let me know if you like this video. Hopefully I'll be doing more of these as the boxes get retired. Like and subscribe. Thank you. Bye.